Alright guys, so this video is about Newton's law of gravitation or universal gravitation. This is sometimes called his fourth law, although it doesn't deal explicitly with motion. Newton was the first one to really put a mathematical expression to this force of gravity, and you guys I'm sure have all heard about the apple falling from the tree and him realizing apparently that the same force that pulls the apple down to the earth also held the moon in orbit around the earth and the earth in orbit around the sun, and so on and so forth. And so from this and from a series of laws called from Kepler, Johannes Kepler, Newton formed his law of gravitation. So what I want to do first of all is just give you the equation for it. And in physics, as you know, we very rarely express our laws in words. We prefer to do that in terms of mathematical equations. So for this law, it's going to have the form, the force of gravity, and if you guys remember, the special name that we give to the force of gravity is called the weight. Okay, so very often we have to calculate the weight of an object. Up until now, we've been doing that by saying, hey, it's the mass of the object times the acceleration to gravity. This will be another equation that allows us to calculate the weight of an object if we so choose to do it. But really what this law is used for is the force of gravity between two separate objects. So maybe like a planet and a star, or a moon and the planet. And really it can be any two masses. But the reason why we usually only use this for bigger objects is because gravity is an extremely weak force. And to show you why that is, let me write the rest of this equation here. So this force of gravity, and this is in newtons, is equal to a constant which we will call big G. This is the universal gravitational constant. I'll get to that in a second. And as I said, there's two masses, so maybe that's M1 and this one's M2. And the idea behind this is whenever we have two masses in the same area of space, they're going to attract each other. There's a force of gravity that attracts these two masses to each other. And so the product of the two masses, and these masses are in kilograms, divided by the distance between the masses squared. Now this distance that we're talking about, it's not the edge-to-edge difference, okay? It's from the center of one to the center of the other. And so we have the center-to-center distance between these two masses. Okay, so it's not the edge-to-edge. Okay, so we're not going from here to here. It's the center-to-center distance between the two masses. That's what R is, and this is going to be in meters. Okay, so distance between the masses, again, just keep in mind this is the center-to-center distance. And again, this will be in meters. Okay, so big G, let's return to big G here. I'm going to draw an arrow all over here because I'm running out of space. The universal gravitational constant. This has a value of 6.67 times 10 to the minus 11th. It's a very, very small number. The units it has, Newton meters squared over kilograms squared. You can kind of see how everything will cancel out. So like the meter squared will cancel out with the meter squared on the bottom here. The kilogram squared on the bottom here cancels out with the kilogram squared on the top here. And we'll be left with newtons. Now, because this number is so small, what that indicates is that gravity is a very, very weak force. It's an extremely weak force. In fact, we don't notice it unless these masses are very, very big. Okay, so we don't notice the gravitational attraction between ourselves and other people, or between ourselves and, like, say, the floor, the wall, whatever has mass, right? We don't feel pulled in all these directions because we don't have much mass. So in order to notice this force of gravity, we have to have a lot of mass. The gravity is a very weak force, and physicists honestly don't know why this is. It's a current. It's probably one of the big questions in physics right now. Is why is the force of gravity as weak as it is, especially when compared to the other fundamental forces of nature, like the electrostatic force and the magnetic force and the strong nuclear force. Okay. So anyway, this is Newton's law of gravitation, and it tells us the force of gravity between two objects. And the reason why we're studying it in this unit is because this force of gravity, you can imagine, it holds objects in orbit. And so that's a type of circular motion. This orbital motion is a type of circular motion. So we're going to use that in some problems here. But first I want to comment on one of the characteristics of this. And that's that it's called an inverse square law. So we say the force of gravity, I'm going to write it out here without defining all the terms, big G m1 m2 over r squared. I want you to pay attention to this r squared here. We call it an inverse square law because, first of all, inverse, this r is on the bottom. Okay, so the force of gravity is inversely proportional to the distance. The larger r gets, the lower this force of gravity gets. So it's an inverse. We call it, the square obviously comes from the fact that this distance is squared. Okay, so this whole thing's an inverse square law. Now I mention this because this comes up a lot in different physics laws. It also is in the equation that tells us the force between two charges. It tells us how the light illumination, how that decreases with distance. That's also an inverse square law. Okay, so we come across these a lot. And the conceptual point I want to make is that if I have two objects, say some distance r apart, okay, we'll just say that this has some gravitational attraction Fg. If I then double the distance between the objects, okay, so I increase this distance, and now this is 2r. Well, because I've doubled r, and then I squared it, so this essentially what I did is I took 1 over 2r and then squared it. This new force would only be 1/4 as strong as it was before because we doubled it and then we have to square the 2, and so this will be 1/4 as great. And so we say that the force will decrease with the square of the distance. Conversely, if we were to get these 2 times close together, then the force of attraction would be 4 times as great. Okay, so this is the nature of the inverse square law. We'll do some problems dealing with the inverse square nature, but let's look at a couple of sample problems just so you guys get a feel for how the math works out on this. So this is a typical type of problem. We have 2 spheres of lead, and they have centers that are 15 centimeters away from each other. And you're given the masses of the 2 spheres, and you're just asked very simply, what's the force of attraction between them? So what's this gravitational force between them? And so we write our Newton's law of gravitation. And so this will be the mass of sphere 1, mass of sphere 2, over the distance between them squared. Plugging in all of our numbers for big G, 6.67 times 10 to the minus 11th Newton meter squared per kilogram squared, times, I'm going to use kilograms, so it'll be 25 kilograms for one sphere, 15 kilograms for the other sphere. And then the distance between them, you have to use meters, so this will be 0.15 meters, 15 centimeters, 0.15 meters. I square that, and if you plug all that in, you get 1.1 times 10 to the minus 6 newtons. Okay, simple enough, right? It can get a little bit more complex. Okay, I mean, that's useful to know. It's useful to know the force of attraction between two masses, but we can also do some, maybe what I think are more interesting things with this. So say that we have a planet, and you're given the mass of the planet, and it orbits a star, and you're given the mass of the star, and you're given the distance of the planet away from the star. And maybe we want to know what's the tangential speed of the planet in its orbit. So we have our little star here, the flames. Okay, so we have our little star, and then we have our planet. Just one face. And then we have our planet, and this is going to be 7.8 times 10 to the 8th kilometers away, and it's going to be going in this circular orbit around it. And the force that's providing the centripetal force is this force of gravitation. So what I can say is that Fg, which is equal to big G, I'm going to say m sub p for mass of the planet, m sub s for the mass of the star, these are the two objects that are attracting each other, divided by the distance between them squared. That has, because it's acting as the centripetal force, and the planet, we're going to say the planet's moving around in the circle, then that has to equal the equation that we have for centripetal force. So we'll say the mass of the planet times its tangential velocity squared. Now this is what we want to solve for, divided by the distance between them. Okay. Now some things will cancel out here. So it turns out we don't really even need the mass of the planet when we solve. This is one of the useful things about using variables, right? We can see things cancel out. So we don't really need the mass of the planet. This r will cancel out, and this one r will cancel out. And so what we are left with is big G times the mass of the star divided by r is equal to v squared. And v would just be the square root of big G mass of the star over r. And at this point, let's plug our numbers in. So we have 6.67 times 10 to the minus 11th Newton meters squared over kilogram squared times the mass of the star. So this will be 4.0 times 10 to the 30th kilograms. Divide all that by the distance, so 7.8 times 10 to the 8th kilometers. Take the square root when you're calculating this, and I got 5.8 times 10 to the 5th meters per second. So this is the tangential velocity of this planet. It's going to be the velocity, it's the speed. In other words, it's the speed that's going around in that circular orbit. Okay, so in this problem, what we saw is that this force of gravitation, we can calculate its value with this equation, and because it's acting as a centripetal force when something's in orbit, we can set this equation equal to the equation we have for centripetal force, and some things will cancel out, and we can solve for the velocity. So we'll do more problems like this in class, and if you guys have any questions, please let me know.